welcome to the stream. My name is Nick Larson, and today we're gonna get back on doing some AI and just chatting about whatever. Ooh, get stretched up here. All right. So yesterday we had a great day, a really great day actually. Some nice people stopped by and helped me identify what a really big problem was with the code um, for one of the tests that I was running that didn't seem to be stopping. So early on, we identified that it was not finding the correct solution because it was searching to a depth deeper than it should have. And so what ended up happening is we got into it and we ended up writing some code to test whether or not the solution state was valid or not. And when we figured that out, what we found out was that none of the states that I was using as a starting state were coming through as valid, and so we had to fix that. The way that we're going to go about fixing that is to change the goal state to more closely match what's in the literature, and then just kind of work from there, really. So that's what we're going to do. And funny enough, we had originally had the goal state this way, and then we changed it. So now we're going to go back and rewrite everything. Okay. Let's see here. First things first, let's go with changing the goal state in puzzle. Generate goal state. Seems like a totally valid thing to start at. Excuse me. Generate goal state. Result. Max tile value. Basically, we just switch this to be greater than or equal to 0. Max tile value. U long of the number of rows and number of calls. So that should change it so that that's the goal state. Then we have expand moves. Same idea. Blank offset. Really just looking for anything that uses goal state. Goal. And what we see up here is goal, goal, goal. Copy the goal. Is the goal compared to, so copy. All right. That should have changed the goal state. Now let's go ahead and take a look at the in puzzle test. Fast.test. In puzzle test. Default initialization. So let's save this. Save this. And let's test the in puzzle to make sure that this is still working correctly. Should not have debugged this. Should have just run it. Terminal output. Seems to have paused. Or we ran into an actual infinite loop. Maybe debugging it was a good idea. Or maybe it's just getting stuck because I had a breakpoint. Pre-launch task build terminated. Okay. Let's go with .NET Build. Okay. Some projects have trouble loading. Please review output for more details. Tasks. Main. Now I'm confused. What's having trouble loading? Okay, well, .NET Build worked. Output, terminal. Let's try and debug one more time. Okay, great. So I equals max tile value. Okay, great. How long do we have to let this go? Why is max tile value 8? 2 1 0. Oh, it's a U long. Oh man, that is funny. Goodness, that's hilarious. Okay. Is greater than 0. That is a funny bug. So then I guess we just want to say result equals this happens out here. And that will take care of pushing the 0. Yeah, let's try that. Okay, we save this. Try and run this now. What a crazy way to have that. Okay, great. They all passed. 3x3, 3x4, 4x3. Okay. Next thing that we want to do is test initialization parsing. This shouldn't change. This should just work still. Okay, great. Those all passed. The next thing we should do is test the Manhattan distance. Now it claims that, oh, these are all going to be different. Wow, these are all going to be different. Okay, let's go ahead and recalculate these by hand. Okay. So the 8 needs to go over 2 and down 2. That's 4. The 6 needs to go over 1 and down 2. That gets us to 7. The 7 needs to go over 1 and down 2. So 8, 9, 10. 11, 12. 13. 14. 15. 16, 17, 18. Okay, so 18 I think is the new one here. Let's do this one. 0. And this should be 0. And then I want to say putting this one here Oops. And putting this one here. Let's see if this works. Okay. Let's go ahead and take a look at this one. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12. Okay, let's take a look at this one. This is a 3 by 4. 3 rows, 4 columns. Whatever. It's frustratingly difficult to look at. Okay. The 3 needs to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm doing this wrong. Let's just write them down. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so the 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So this one's 24. And then a 4 by 3. Make this a 4 by 3. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay, and then this one should be 35, but we're just going to do it by hand anyway. All right. Okay. Eight, 9, 10, 11, 12, 13, 14, 15. Okay, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 35. Okay, great. Now let's test all of these. Failed. Didn't I just do these by hand? How did they all fail? Oh, I know why. Because I put the blank row and blank call in the wrong places. Equals 0 and 0. That's right. I should just write a function here called find 0, and then I never have to worry about that when I change other stuff again. Okay, I saved that. Let's run this one more time. No, it's still failing. Oh, that's right. Yeah, got to change that. Okay, so the expected location starts at 0. In puzzle, Hamming distance expected 0 UL. If tile value okay. So now we can say expected plus plus. Same thing here. Manhattan distance expected. Expected cell location. Expected cell location. What is this? Is tile value. I think it's just tile value. Tile value. Yep, just tile value. Let's try that one more time. Build it up. Okay, one failed and the rest passed. Did I calculate this one wrong? 18 and it should have been 19. Yeah, I believe I calculated it wrong by hand. Let's try it one more time. Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8. 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, no, 19. Yep, okay, 19. Alright, I just counted wrong. Save those. Run that test. Okay. All right, 6 passed. Now we want to do the is solvable test. And I believe that the answer on all of these is not clear. Not clear. First, let's just run it and see if we're wrong. Yeah, we're wrong on all of them. Look at that. Okay, we passed 4. And we failed 5. One of these I swapped yesterday. I want to say it was this one with the 11 and the 3. Let's go take a look. I think this one is going to be I'll open recent Corf puzzles. Okay, 3 and 11. Three and 11. 11 and 3, is this it? Did I just swap the last two? Let's see. Nine, 14, 5, 7, 8, 15, 1, 2, 10, 4, 13, 6, 12, 0. Yeah, I just swapped these. Okay, so this one should actually be false. Those should all be true. Now let's see if we can figure out which ones are passing and which ones are failing. Let's see if we can figure out which ones are passing and which ones are failing. Okay, KC. True. 3, 11. Okay, let's run these. Oh, and we failed all 7. And that is because we need to change the parity. So this is inversion 0, add 4, that's even. So this has to do with the parity. Equal initial state is solvable. Okay. That's the goal row. And then let's just see if this passes all of these. Okay, great. I don't want to actually output this stuff anymore. And then let's see if these now work. And let's run that. All right, 10 passed. Clear. Okay, so at this point, What we want to do now is we have tested to make sure that the state is in good working order, and we want to get back to testing whether or not the... Actually, yeah, before we get crazy here. Before we get crazy here, all right, let's get rid of this. Let's just go make sure that the solver can solve the easy ones. Like, for instance, this one. Run test. Okay. And it found the goal because it's actually 27 moves. Oh, that's interesting. How'd my cost end up at 27 and my final state end up at 29? If I pop off, let's go look at the goal. Solver. That's really interesting. Before I check if it's the goal, I do this and then I rebuild the solution. So somehow the output is giving me 29 moves. Somehow the output is giving me 29 moves, even though it says it's only evaluated 27 moves deep. Oh man. That's just really frustrating how everything keeps going like this. Let's try it again. Let's just try it again. You know what? Let's not try it again. Let's go try one that we know how long it is. And let's see what's going on. We know that this one is 45 moves. Let's just see how long this one takes. Wait, nope, this isn't what we wanted. Stop! Okay, task manager. We know that Visual Studio Code is running this thing. We want to kill this like that. Okay, there, that ended. What we want is this one, which we know is 45. Come on, you can do it. Oh, there we go. All right, cost 45, and it found 45 moves. Perfect. Okay, great. Okay. Now that we have that, why is it taking? Why is it doing something crazy for these other ones? This happens in 45. Great. That happens in 45. Test solver. Okay. And what do we have to do? 133,000 states? That's not too bad. Took about 3 seconds. Okay. I wonder what this one's going to end up doing on the Hamming distance. Let's just try this. Okay, that one found 27 moves. That's really interesting. So somehow when we run... Oh, that is a little silliness. Okay, so in my A star, when I find a successor, I say came from. Okay, so this is wrong right here. If now I need to know if it improved it. So this needs to be a bool, which needs to go up to IOpenSet and needs to change to bool. All right, the idea here is I need to know whether it was an improvement or not in order to change the came from. So that's what I need to update. So this is return false. And then basically everything else is return true. Return true. And then what I say is var was improvement equals and then I say if was improvement, then do this. Now let's see if A star works. All right, 27 moves and a cost of 27. Perfect. Exactly what we were hoping for. Okay, this is great. Let's check all this in. Let's check all this in. I don't want to go too fast. I want to save everything. Okay. This is actually 2 bugs. In puzzle test, A star search solver. Unstage everything. IOpenSet. Okay. Only update came from when state was improvement. And then the other thing we did here is change goal state to match literature. Hooray! Okay, that's great. Okay, so now we have that rolling. And okay, this is great. Let's take a look at the to-do list for our first time. 2000 19020777. Yeah, there we go. Change the goal state to match the literature. Fix bug in open set. No, in A star. That was improving. I need to fix that in another place as well. I need to fix that in the breadth first search, don't I? No, actually, I think breadth first search gets away from the need to do that. But we're going to do it anyway. And a reason that I think this is because there's only unit cost, so it doesn't matter which one you came from. But since this is sort of a confusing optimization to have here, I'm just going to say was improvement. And then I'm going to say if was improvement, then do that. Okay. And then let's commit that as well. Which one did I do? Only update. Yeah, okay. Consistency changes for was improvement. Commit. Okay, great. Okay, great. That's good. All right. So, what do we do? That's a great question. What do we do now? Let's take a look. Let's take a look at the to-do. The to-do list, open set returns true, false for was improvement. Okay, great. All right. Implement the to-dos, animation showing how to solve it. All right, so at this point, we have gotten to the point where our heuristic for solving this is doing just fine. If we choose a little bit of a harder problem, what we're going to notice is that it's going to take a good bit longer. So let's go ahead and do that. Let's find us a nice medium-sized problem like this one right here, which has 50 moves. And let's go take a look at this one. In puzzle, solver test. Okay. If we take a look at this one, and it said that it takes 50 moves to solve this one. Let's just double check that. Oh, great. Which one was it? 4, 3, 6, 13. 4, 3, 6, 13. Yeah, okay, 50 moves right here. All right, so this one says it should take 50 moves. And because it takes 50 moves, it should run for a little bit longer. And this time we get to watch the actual output. Let's trash all this. Great. Let's save this. Let's run the test. When this pops up in here, we'll just sort of watch it run. And let's see. All right. So in the first 10 seconds, we did 293,000 states. I'm expecting this to make it to around 1 million states, which is going to take a few minutes. Yeah, in the last time period, it really slowed down. So this is where we want to figure out how to increase the speed of the open set. Or the other direction we can go is to just get rid of the open set altogether. So the way that you get rid of the open set is you switch over to using what's called iterative deepening A star, which is like instead of doing more of like instead of maintaining a closed set, we don't actually care that we've ever visited something before, if that makes sense. We're just going to evaluate everything up to a certain value, And then when we have exhausted everything up to that value, we're going to increase the value to the next highest value that we saw. And then we're going to do that. You'll notice that, like, as we are watching this, it starts out by going to 42 and it finds a bunch of states at 42. Then it goes and finds a bunch of states at value 44, and then it finds a bunch of states that eventually it'll get to 46. The reason it increases by 2 here is, I'm not actually sure. It's very related to this problem, though. I've seen this a number of times. But we know that the answer here is 50. And it's gonna take a while to get there. I really thought it would have found the goal by now. Let's see, was this one 70 million or 7 million? 7 million. Okay, so this only had to view 7 million states, and it's viewing a lot of these states over and over and over again. Yeah. Now I'm actually quite confused. Oh, you know what? Node expansion. It's got to do with node expansion order. Let's see. The way that we're going to solve this is we're going to go look at my repo, and we're going to see what the ordering was on the repo. So GitHub, Nick Larson. Let's go to heuristic search. Zoom in so everybody can see. Source, InPuzzle, not pattern database, successor list. Maybe? No. Where's the actual A star part of it? Program? Maybe it's just in program. Breakdown, fast ID A star. Puzzle. Let's see, where is the thing where I expand it? Solution equals algorithm. Print solution. IDA star driver. IDA star. IDA star successors. Expand state 1 blank. Expand state 1 blank. Okay. Create successor. Create successor. So it looks like we're going down, right, left, up. If we change the order of these, it should match a lot closer. Down, right, left, up. That's what we want to do. Okay, let's do that. Down, right, left, up. Down, right, left, up. This still hasn't finished. It's going very slowly at this point. You can see it's only doing about 2,000 states per second. But it is up to 46, and we know that it's going to get to 50. Down. Let's go ahead and change that. Down. InPuzzle. Expand. We want to do up was last. Down. Let's see. Of course I had to close that like an idiot. Reopen, close tab. Down, right, left, up. Down, down, right. Left, up. Okay. Okay. Let's go ahead and save that. Okay. Expand in same order as Corf paper. Commit. Great. What's this? Try a harder problem. Nah, I gotta save that one. All right. So the interesting thing here is obviously this puzzle takes a little bit of time, and that has to do with the number of states that it has to search through and how fast it can search through those states. Now is a time when I would really like to have a... I would just really absolutely love to have something to tell me what's taking the most amount of time. A little profiler would be nice. And part of me really wants to pop this into a profiler in Visual Studio just to see if there is an obvious problem. But in any case, let's go ahead and stop this. And then restart it with... All right, let's restart it now with the updated expansion order. And see if we get to a higher number faster. So notice that it took us about more than 400,000 to get to 44. And then it took us about 1.3 million to get to 46. So we're looking for, all right, we already found 44 before 390,000. And that's compared to the 450 that we needed over here. Okay. All right. I just want to let it go a hot minute to see if it can get a little bit further. Do I pop this into a test? Do I pop this into a profiler? I feel like up to this point the answer has been no. And so I probably want to keep it at no. I probably want to keep it at no for now. See if this gets to 46 before 1.3 million. All right, and in any case, one thing that you should notice is that we did 29, almost 30,000 states per second. Look at that, it really jumped back up. That's pretty crazy how it does that. But we did almost 30,000 states per second when the sets that we were looking at were very small. So if we move to a point where we don't have to maintain the sets at all, we ought to be able to view a lot more. We're going to do a lot more work, but we ought to be able to view a lot more. And let's just give that a shot, I think. So we're going to break 1.3 million, it looks like right here. But imagine if we could do 100,000 a second. In the first 10 seconds, we would get all the way to here. So let's give that a shot. I think IDA star is the next thing we want to try. Actually, before we do that, I think I want to make this solver generic, because we're going to get to the point where we're going to have to change a lot of stuff if we don't take care of that now. So I do think that's the next thing we're going to do. And what I mean by generic is we want it to be able to solve any problem. Not just, oh, there we go, we finally got there. Okay. All right, I'm going to go ahead and kill this. And then what we're going to do is we're going to make this generic. And then after we're done making this generic, we ought to be able to apply any problem to it. Okay, so let's go up here. And what we want to do is say iSearch algorithm, and this is going to take in an iProblem. So let's extract iProblem first. New, let's just keep it here. Public interface iProblem. Now problem needs to have a few things, which is taking a look at the in puzzle. Actually, I don't even want to take a look at the in puzzle. I want to take a look at the A star. Given a problem, I want a state. Do I want to... Really what I want to do is say iProblem state. And when the things that I want to do here are get actions, iProblem action, public interface iProblem action. And then this is going to be iProblem action I void apply action, iProblem action. I guess technically, like, having just integers here would be an easy way to go about it. Although that's not always possible. If you have like a continuous space, yeah. Having non-discrete spaces is not exactly what A star is for. Okay. This needs to be action. And then we want iProblem action I guess array expand. And this is really just like a holder template. Okay. And then this is going to be iProblem state. problem action array of I problem state initial. And then I want to say I problem state goal as well. Yep. Okay, so now everything's broken. So let's make first in puzzle implement I problem state. Or really, let's just make A star work with this. So I search algorithm. T of T, T problem. T problem, where T problem is I search state. Why is that not working? I problem state. Does not implement this interface. Okay, that's great. So now I want to say I problem action. Then I want to say I problem state initial. I problem state goal. Okay. No, let's put the goal in there. Bool is goal. Okay. So we no longer need this. Now we need I state cost. We don't want this to be puzzle. We want this to be T problem. Okay. I don't want this at all. I didn't realize how much there was going to be to change. This is a good idea to do this early on. Okay. A star state cost. T problem. T problem. Okay. Now instead of this, we want this to be T problem. We want this to be T problem. Okay, that takes care of two of those. And then T problem. Not in puzzle. Notice we're never calling this because that is incorrect the way that it is right now anyway. Okay, I think that'll do that one. State cost. Requires... oh yeah, state cost. This is where T problem is I problem state. Still not helping. T problem. Initials. Initial. State. Came from. Dictionary. I don't want these to be. I want these to be T problem. T problem. Let's just copy this. T problem. T problem. I problem action. I problem action. Okay. T problem. Okay. Rebuild solution. Let's just call it expand. Yeah, we do want move copy here. Yes. We do want move copy. Okay. We do want move copy. State cost. T problem. I search algorithm. Apply action copy. I problem state. Apply action copy. Okay. And this is apply action. Oh, great. I can no longer guarantee search algorithm. I problem state. I can no longer guarantee that that's the same. Wow, I don't know what to do. Let's go with T problem. So the specific problem that was passed in is a problem state. Okay. This got wholly complicated. Maybe the better way to do this is to start fresh. Probably not. Basically, I have the rules. Let's do the easy ones first. I problem action. Problem action. And then I want this to be T problem. T problem. I problem action. T problem. I problem action. Okay. So now the only thing that I need to do is make it so that a problem okay. I problem. So we're going to have I problem. Public interface I problem T state where T state is I problem state. Okay, now what we're going to do. Yeah, okay, all right. Now what we're going to do is have this have the rules. Is goal T state state and then this is just going to have I problem state copy and then we're just going to have T state state now if you want to copy an act you got to do two different things and then expand as well. Okay, I think this is more along the lines of what we're looking for. And then what we want to do is we want to say expand T state state. I think. No. I need a copy. Okay. T state copy T state. state. And then that's guaranteed to have a copy. I think this is more in line with what we're looking for. And then what we want is iProblem. We want this to be generic. T-problem, where T-problem is iProblem of T-problem of T-state, where T-problem T-state, no, T-problem T-state, where T-problem is iProblem of T-state. Why is that not working? T-state cannot be used as a I don't know how to do this. I just want it to say, like, there's a couple of actions that you have to be able to do to implement some rules. And then that's that. And for some reason, I can't seem to figure that out. Let's see. T-problem. Solve T-state. What's the problem here? The type T-state cannot be used as a parameter T-state in the generic T-state. T-problem. How about iProblem T-state? Let's try that. And then I don't need this where clause at all. Where T-state is iProblem state. iSearch algorithm T-problem where T-problem I don't understand. T-state? Why not? iSearch algorithm for a problem There is no boxing conversion or type parameter conversion from T state. Okay. Solve. Yeah, that's the only thing I want to do. I want it to take in how about we just make this how did we work this out? Type or namespace T state could not be found. Honestly, don't know what I'm doing here. All right. Your search algorithm only has a thing called solve. And it gets a problem definition from the type parameter, or you pass in the rules as well. Yeah, let's pass in the rules as well. So then I don't need this to be generic at all. And I can just say that this is I problem of T state. Why is this complaining? Type T state. T state and the generic type or method problem state. There is no boxing conversion. I really just don't get it. Oh man, I'm just having a rough day. Don't understand what I'm doing. Okay. Let's see. You can give it any problem. You just need a definition for a problem. Where T state is I problem state. Hey, all right, that's an improvement. Okay. So now I can pass it the rules like this. Let's see where this has gotten me. Great. A star search algorithm T state where T state is I problem state. Okay. T problem T state. No, I problem. I problem T state. And now I want to rename T problem to T state everywhere. T problem T state. Problem. Let's get initial. Okay. I problem state. No, T state. Get initial state. Great. let's call this problem. And then let's say var initial state equals problem.get initial state. What's your problem there? iSearch algorithm. Nope, didn't want that there. Wanted that there. Great. Okay, so now you have the initial state. And then you say push or improve. All right, so we have now added the initial state. Okay. While not openset.isEmpty, pop min t state, where t state dot is problem state. Problem state should have an is goal. No, the rules should have an is goal. So problem dot is goal state problem dot expand state. Rebuild solution came from copy that. T state. Should just copy this because that's going to happen over and over. Okay. I think that's doing okay. And now what I want is successor equals state dot copy, and then problem dot apply action to successor action. Copy. I don't want this to be iProblem state. I want this to be on the problem. Okay, that's it. I need the problem to be able to do the copy. So I don't want problem state.copy, I want problem. Problem.copy. Of state. Okay. Hey, what's up, man? Oh, I don't have uptime working, do I? I've been around for, God, what is it? I guess just shy, about an hour and a half, a little shy of an hour and a half. I'm having a rough day today. I am trying to, like, take care of some cleaning up of things before I like start adding more algorithms, sort of making them generic, right? The idea of A star search is that it can't just solve one problem, it can solve lots of problems, and you just like abstract away the like concept and the things that define a problem. And I had already gotten myself to the point where I was so far beyond that like it's turning into a real process to get it to be generic. And so that's just what I'm grinding through right now. Oh. Anyway, how's your day going, man? Oh, goodness. Okay. So this heuristic needs to not be in puzzle, needs to be T state T state. All right, I think I've got A star working. Just got home. Man, do it. Absolutely do it. I mean, if you have the time, of course. But yeah, definitely recommend it. I get off around 4 today, my time, so about 2.5 hours from now. Be nice to have something to do right after work, other than listening to my kids. Could hear them screaming upstairs right now. Oh, excuse me. Ooh, goodness. Dropped a little water there. Anyway. Okay. Just like 18 more things to solve. And then I can get back to the point of trying this stuff out. Let's go ahead and fix the test. Delete. I feel like the tests are actually not going to be that troublesome. Oh, I see. In puzzle. Ooh, goodness me. Ugh. Just kidding. Okay. So I need to define this in puzzle as an I problem. T state. No. Of in puzzle. Where, oh goodness me. Okay. Okay. This was working just fine. Public class in puzzle problem, which is an I problem of in puzzle. Now the problem with this is in puzzle needs to now implement I problem state needs to implement I problem state, and it needs to have a copy operator. Okay, that's fine, we can do that. Where's my copy? Expand moves. Move copy. Great, let's do public in puzzle copy. That's, yeah, in puzzle copy. And then it's just this. Return that. Now that should implement what it needs to implement. Oh, but it doesn't. In puzzle.copy cannot implement iProblemState.copy because it does not have a matching return type of iProblemState. That's great. I don't know how to do that. Yes, I do. iProblemState of T state. T state. That's kind of recursive, isn't it? Whatever. T state. And then I don't actually need this anymore. Where problem of T state. Okay. Now what I have is I problem state of in puzzle. Okay. Okay, great. Now let's implement this interface. Okay, we gotta just move everything, basically. Back to A star and fix all the red here. Now we just want state.copy. Why is that not working? T state copy. Because this has to be of T state. Okay. T state cannot be used. Cannot be used as a type parameter T problem in generic type method T state T problem. I don't understand why not. There is no boxing conversion or type parameter conversion from T state to I problem state. Oh, it's because, got it. I problem state of T state. That's not what I wanted at all, is it? T state. Oh, that's not T problem. We're going to change this to T state everywhere. T state, T state, T state, T state, T state, T state, T state. Okay, back to this one. Back to this one. All right, all green. Okay. In puzzle. Now what we're looking for is to move all of the stuff from the state to the rules object. Okay. Okay. How are we going to do this? Goal. I think so. In puzzle. Okay, this is all gonna break. Everything should start popping up red in a minute. Public in puzzle problem. Puzzle problem. Generate goal state. Let's move generate goal state. Generate goal state. Okay, great. In rows, in calls. Int in rows, int in calls. Okay. Int value bits equals 4. Const int value bits equals 4. Okay, I think what we're going for now is that gives us the goal, and now we should be able to implement is goal. We should call this in puzzle. Nope, we should not call this in puzzle. Yeah, we should. In puzzle goal we're going to come back around to that. But essentially, the idea now is to say, I don't know how to get access to the internals without just making them straight up public. Which I'll probably just do because I just want to get to the end of this before the end of the stream. Okay. In puzzle. In puzzle rules. Maybe the goal... Yeah, maybe... It was kind of nice having the state this is no longer here. This needs to be up here. Okay, we can do expand for sure. The state. What if we just left all this here? Yeah. You know what? Let's do it. Let's do it like that. Let's do it like that. Let's leave everything in there, and then we'll just have everything pass through. I'm okay with that. Okay. Okay. Get initial state. That's easy. Return new in puzzle. This needs to actually have... Okay, so private int in rows in calls public in puzzle problem int in rows int in calls this dot in rows equals in rows this dot in calls equals in calls. Okay. And actually we can just make these public in rows get private set calls in rows in calls. And then when we say give me this, we just say in rows in calls. Okay, great. There we go. Then we can just say return state dot expand moves. Yeah, let's make that a list. A list of this. That actually makes sort of more sense. iProblem action. So what we want to do here is go to iProblem, and we want this to be a list. Why is that complaining? List. Sure. Okay. And then expand moves, because in move.location just needs to have in move just .location needs to have this marker on it, iProblem action, that does absolutely nothing except cleans it up. No, you can't do that. Why can't I do that? Cannot implicitly convert type of in puzzle.location to iProblem action, even though it is a problem action. That's hilarious. So list of locations. I thought these were supposed to be like covariant. So my location is an iProblem action, and yet I cannot assign a list of iLocation. That doesn't make sense, does it? Let's take a look. Class tsnap. No. Oh, that's why. You have to call it like no. I ought to be able to just do this. Interface interface A. Hi. I don't even care about anything else. Class B, which is an A. Public int hi. Get set. Now I want to say list of A stuff equals new list of B. Huh. What? Cannot cannot implicitly convert type. CS0029. CS0029 cannot inverse. Solved with. No. Okay, let's just do C# list of interfaces cannot implicitly convert type. List contracts iProduct. It's a covariance limitation in C#. You can't convert a list of one type to another. Instead of this, oh, interesting. Huh. Thanks for your help. I really thought you could do that for some reason. Oh yeah, this is a long time ago. But not supported in constructs that have both in and out channels. List T is such a construct, so they do not support contra and covariance. It would work if you were using IEnumerable. Well, hell, I don't have a problem with using IEnumerable. Let's use IEnumerable. Everything's already screwed up anyway. IEnumerable. Oh, what's up? Did you see how easy that was? Now we just gotta go change this. IEnumerable. That's hilarious. Okay, that makes sense a little bit more. So because you can add to a list, it has an in parameter, and you can only have contravariance when you're getting things out. So you need an interface that has no way to add things to it, only to look inside of it. Okay, that makes sense. Okay. State.expand moves. Apply action. State dot move action location. Oh, I can't do that. Ooh, that's ugly. Okay, that one's kind of ugly. So I am gonna have to change that. Basically, we're just going to change this to be action. And then we're going to have return state.isGoal. All right, this is a really hacky way of doing this, but for the moment, like, everything's fine. So we can't do location here. We have to do problem action, and then here we have to do location action new blank location equals location of action. Okay. Where is it complaining up here? Because you forgot to tell it you're done. All right, I think we've gotten to the point where this will work. We implemented a copy, right? That was one of the things that was sort of outstanding. let's just say copy equals copy. Okay. This isn't even actually used anymore. Yep. Okay, overall, I think this is going okay. Okay. Now we need to update. First off, is anything broken in here? No. This seems to not like. Okay, so this needs to be search algorithm of in puzzle problem. Let's see, how did I do this with A star? Search algorithm, oh yeah, of T state. Yep, that's it. T state. Constraints are not allowed on non-generic T state. Okay. T state. Get rid of all of these. Problems action. T state. Problem action. State cost of T state. Default of T state. Okay. Still going. Oh man. Basically all of this can be copied. The is goal problem.isGoal successor. Problem. Oh yeah, that too. Problem. And then you need this initial state thing. Okay. And then state cost of T state. And then open set dot push or improve. Oh, this is wrong. What is going on? Where am I clicking? These definitely need to be there. And then it's this right here is okay. Like that. And then we just want to redo rebuild solution to be T state pretty much everywhere. T state, T state. And then we want not in puzzle, problems action. Problem action. problem action. Alright, is that it? Control F in. Okay, I got rid of all the end puzzles. Did I get rid of all the locations? I did get rid of all the locations. A star. Control F in puzzle. Ooh, I did not get rid of these. That's right, I did not get rid of these. Okay, so let's have apply action in puzzle. Apply action needs to return. For now, it's just going to be an int. Return state cost. Return in puzzle dot step cost. Okay. And then instead of this, we're going to have int action cost. No, step cost. Apply action. I put that on the problem, right? I didn't update the interface. Int. That's something we'll have to worry about later. How to actually wrap that up. For now, step cost. There should be no in puzzle anywhere. Breadth first search solver. Apply action. And this is int step cost equals, and this is step cost and step cost. Oh my. And for this, we just want in puzzle problem. Oh, I really thought that was going to be it. Cannot be used as a parameter. Oh, no, in puzzle. Okay. In puzzle. In puzzle. I search algorithm of T state. Oh, come on. Of T state. Solver type T state. I search algorithm of T state. Oh, come on. You need to make it so that that takes in. Solver. Okay. The search algorithm is an I problem of T state. Does it work if I just put in puzzle here? Okay. And then the only thing that happens is this doesn't work. Okay. I need a way to define the initial state when I instantiate the problem. Okay. Oh. Let's go take a look at these end puzzle tests. There's no way these can be working. Hey, look at that. They do work. Because I didn't do those generically, it's testing end puzzle directly. I am creating a solver for a particular kind of state. Now I need a problem. You know what? Let's just do it like this. Let's just say var problem equals new in puzzle problem 3 3. Let's just copy all of this. I know you don't like that. We're gonna do it anyway. In puzzle problem. Okay. We're gonna say string initial. Wait, nope. Here we go. Get initial state. Okay, here we go. All right, now we're making progress. How about we just have a gets? No. Okay. Private string initial state string initial state equals null. This dot initial state equals initial state. It's getting kind of ugly at this point, huh? And then down here we say if initial state equals not equals null, return new in puzzle of in rows, in calls, initial state. Now we can go back here and we can create one of these. And then instead of all of this jazz, we can just say problem. Solver problem. Got it. Okay. Problem. Problem. Then we can say for like this. I can just say problem. Oops. solver, problem, expected. Int expected equals 45. Okay. Yep. Two, three, four. $50, $37, $31. Okay. Three by three, 3 by 4, 4 by 3. I guess we don't actually have that second one there. 4 by 4 and 4 by 4. Get rid of this, get rid of this. Get rid of that one, get rid of that one. Starting to run pretty long here. Get this problem done. I problem. I problem of in puzzle problem. Okay, great. This is not it anymore. Stopwatch, set up all the jazz. Problem. Puzzle. I need the initial state. Okay. Var puzzle equals initial state equals problem dot get initial state. Okay. Look at that, everything's green. I wonder if it builds. .NET build. Oh man, that's crazy. Wow, I've just been coding for like an hour and 15 minutes and then it built. That's awesome. Let's see if it runs. Let's do something simple first. Solver tests are really the only one that we care about. Let's try, not this one. Let's try this one. I have no doubt in my mind this is going to fail. Just not one bit in the world. It took it 27 moves. But it found the correct state. Let's do one of these harder ones. I'm going to lose my mind if this is right. I mean, I am going to lose my mind. If after all of that it worked, whew. 45. my. Wow, I am over the moon right now. Wow, all of that work and then it worked on the first try. Wow. Wow. Okay. That makes me happy. Okay. So, just a real fast recap because I'm way over time and I need to get out of here. Yeah, basically, woohoo! uh, the gist of what just happened, and this is done in a very hacky way, is we removed every single reference to the actual problem of in puzzle from the solvers themselves. So if we go to like A star and we search, oh no, I pressed a button, and we search for in puzzle, we see nothing in here. So nothing related to the actual problem that we're trying to solve is in the solver now. So we have like separated these concerns entirely by just abstracting away the concept of a problem and then saying, okay, as long as a problem has this definition, I can solve that problem. And so any problem that we can cram into that box, A star ought to be able to solve now, which is great and makes me feel awesome. God, that makes me feel awesome. Okay. Okay. That is so great. Holy cow, that's great. Okay, so tomorrow, I'm going to write this down before I forget. Probably not going to forget what we did. That was pretty impressive. Well, I was impressed, but I was also very happy that it worked. Okay, make the solver generic so it can solve any problem. Thanks, man. All right, make the solver generic so it can solve any problem. That's the big one. And then that's it. There's also no constants in here. That was another thing that I had been meaning to do, which is if you go look at the search thing, when you apply an action, it now tells you how much of a cost it costs for you to do that action. So it tells you, oh, I have this action available, but it doesn't tell you how much it's going to cost you to do that action. Now you know after you perform the action, it says, oh, it cost you, one time step or something along those lines. But previously, these A star implementations would go out and they would grab the step cost directly from the end puzzle, and now the step cost is just returned to you from the problem. So whatever the problem is, we can alter the step cost per individual step now. Or per individual action, I guess I should say. And this is going to be great because later on when we solve other problems, the step cost is not going to be the same for every action. Okay, this is great. Okay, I'm going to go ahead and call this here. I'm going to wrap this up and get all this code checked in. And then that's going to be that for today. Wow. Wow, that was a lot of work that eventually worked out. Okay. Make the solver generic. The solver interface generic. Now let me just double check. The only place that there should be anything related to in puzzle should be in the test and should be in the test, which there is going to be, and should be in puzzle. There should not be in anywhere else. Okay, not in here. Not in here. Not in here. And this is the big one. Okay, not in here. And not in here. All right, great. The only place that in puzzle is defined is in puzzle, and then the tests are the things that actually wire everything together. All right, that's it. Thanks everybody for joining. This took a lot longer than I was expecting it to, but this is a pretty big step as far as getting us being able to expand this to other problems. So I'll be back tomorrow, and tomorrow we're going to implement iterative deepening A star, and we're going to run this again, and we're going to see that it should be a whole lot faster. Whereas this one takes a few seconds to solve some of the harder problems, it should only take a couple milliseconds to solve just about any of these problems anymore. Thanks for joining, man. Have a good one. And if you do a pop-up stream, just tweet it, and I'll come check it out later. I would love that. All right, I'll see y'all.